Good afternoon. Thank you for joining our ultrasonic matrix array webinar. First, I'll tell you a little bit about myself. I have a PhD in engineering science and mechanics from Penn State University. I did work in guided wave ultrasound during my PhD. And since then, I've had various technical roles, many of which involving phased array transducers, transducer development of applications, in stints at beginning at Crockrell Branson as a transducer engineer, working at GE's Global Research Center for 10 years, working for GE Inspection Technologies, and finally my current role where we've started a new business here in central Pennsylvania developing ultrasound-based transducer products and installed sensor products, and as well as RVI equipment. The talk today is about matrix array transducers. The general outline is I'll give you a company overview, a brief introduction to phased array. We'll talk about matrix arrays, types and benefits, some specific aspects of transducer construction as well as modeling, an example application, moving into some advanced concepts and the future that could be present for our matrix arrays as evidenced by medical ultrasound, and finally some conclusions on the topic. So we're Sensor Networks, located here in State College, Pennsylvania. That's where our headquarters and manufacturing operation is. We also have sales offices in Houston, Hong Kong, and Osaka. We started in 2014. Primarily, we're offering 3 product lines. The one I'm talking today about is our work in manufacturing of ultrasonic transducers, including standard and custom single element transducers and phased array transducers. We also developed and sell corrosion monitoring equipment using ultrasound, and we have a remote visual inspection product line offering pan-tilt zoom cameras as well as retrieval tools. We're currently about 70 employees. So to give you a brief introduction of phased array, really what the benefit of phased array is, we're trying to replace a static aperture that we would get from a conventionally designed and built transducer with something that's electronically controllable. And we do that by taking that piezoelectric material and making, instead of a single sort of monolithic element, we make many small elements that are individually electrically addressable and controllable. This allows us to get electronic control over the sound field, whereas a conventional transducer has a sound field that is completely dictated by the design of the transducer, the aperture, whether it's got a focusing lens or things like that. Now we can, by having these discrete elements, we can gain electrical control. That allows us to steer the beam, that allows us to focus the beam, and we can also position the beam by indexing through sets of elements in a larger array transducer. Generally speaking, instrumentation uses what's called delay and sum beamforming. You also hear the term focal laws to control the beam. So this slide just goes over a little bit of delay and sum beamforming. The graphic particularly shows you from the perspective of the reception operation, where sound can emanate from a scatter or point in a material, and the sound arrives at all these discrete elements, and therefore the electrical signal that is created from the piezoelectric element is not in phase. All of the elements have a slightly different arrival time because of the different path length. We can apply delays to align those signals, and we sum them all together and therefore generate a single RF line that represents, in this case, focusing of the sound at that particular point. And this works, although this graphic shows you the receive operation, this works equally well for transmission, where we delay the transmit pulses and therefore create waves that will focus at a point. So in general, we apply delays to create an angle, or synthesize the operation of a wedge. Basically creating the pseudo curvature electronically to focus the beam, or both. And as already mentioned, we can index through sets of elements to also move the aperture. Generally, some of the things that we can envision doing with phased array are scanning, as I mentioned, changing focal depth of material, the center graphic about dynamic depth focusing. Sometimes transducer, the active aperture can be not the same for the emission and the reception, such as in the tandem scan shown there. And of course, beam steering and sweeping of the beam by steering. So before we move into matrix arrays, we'll just kind of set the stage with linear arrays. So this is sort of a sketch of a typical linear array where we have an azimuth or scan direction, an elevation direction. And the idea here is you really have an active and a passive plane. So in the azimuth direction, we can do things like steer the beam, focus, as we've talked about. We can index through the array, create scanning. Whereas in the elevation direction, the sound field is completely dictated by the design of the transducer, the aperture, the focusing lens, if you have one. And so it's static and doesn't change. It's dictated by the design of the transducer. So moving into matrix arrays, the idea is to create a secondary axis of beam control. And classically, you'd think of a 2D array as having an equal pitch in both directions. So I have a square element, a group of square elements. And then having that secondary axis, now you can control the beam in basically all three dimensions. You can steer in the azimuth plane, you can steer in the elevation plane, you can focus out into the part. So the whole idea and benefit of a matrix array is to have more control over the beam than you would otherwise have with a linear array, where one axis of the transducer is completely static and dictated by how the transducer is designed. So in reality, we typically, while we do use 2D arrays in industrial applications, we typically oftentimes we back off of a full 2D array with equal pitch in two directions to one of these other variations of that general theme. So, this shows, this figure or graphic shows you the elevation direction, the elements across the elevation, a continuum from the 1D transducer all the way at the left to the 2D at the right. And what we find is that there's sort of middle ground that allows us some beam control in the elevation direction, but it allows us to more efficiently use the channels and optimize the system. So moving from left to right, of course, we have the 1D transducer. 1.25D is where there's an active switch in the transducer that turns rows on or off and basically modifies the aperture of the elevation that can be used to move the focus. It's symmetric about the center of elevation, so it cannot steer. This is one that I've seen in medical transducers, but not in industrial transducers, because most industrial transducers don't have any kind of active switching in order to do this. So the more typical things that you might see then are, again, moving from left to right, the 1.5D transducer. Here, the elevation is wired in pairs of rows. So essentially, this removes the ability of the transducer to steer in the elevation plane, but it does allow you to focus in the elevation plane, and it allows you to move the focus. So it gives you a dynamic control over the elevation and the focusing. 1.75D is where the elements are usually larger than the full 2D case. There may or may not be a focusing lens. So now we have, instead of the classical 2D, square-shaped elements, these would be more rectangular. It will give us limited steering and focusing in the elevation plane. And again, why you have all of these different variations is just the simple fact that 2D arrays are very expensive from a channel count perspective. So, as you go to full 2D, it has, of course, the most performance, but it has the highest amount of elements. It has the highest amount of system channels required to operate. And, these other types of architectures allow you to get a lot of the functionality that you want out of a 2D array, but with a more optimized use of the channels that you have available. There are other types of geometries that could be considered or would be considered 2D arrays. Segmented annulars, daisy types, sparse or random arrays. Again, these are usually designs that the idea is to optimize the use of channels. Sparse arrays, for instance. The daisy and segmented annular are really geared around particular test geometries where that type of transducer makes sense. And I'll actually show you an example later of a bolt probe application where we've developed a segmented annular for that application. So moving into the transducer, there's more so than linear arrays. Matrix arrays have you have to consider a lot of trade-offs. You usually don't have as many channels in the instrument as you'd like to have full control over the beam in a full 2D array. Conversely, you oftentimes don't need to have full control in 2 dimensions. So it really becomes a trade-off between the channel count, the size of the elements, the aperture. For a given aperture that may be required to achieve, near field distance and focusing in the part, we have to decide how to break that up into a number of elements and give the appropriate performance. In general, with 2D arrays, the elements have smaller area than a linear array would conversely, and that really causes very high electrical impedance of the elements oftentimes. So whereas a linear array would often have 200 ohms or so impedance, plus or minus, we can get into having many hundreds of ohms or kilo ohms of impedance with a 2D array, and that drives some different decisions about materials and how the transducer is constructed. There's certainly challenges with the interconnect, and as the elements get smaller and higher density, it can be very challenging, and it requires different manufacturing techniques, as well as we get into cables and connectors. And while most current systems offer connections for up to 128 channels, sometimes as you get to have more elements than is supported by the connector, you have to go to multiple cables or custom connectors. This slide talks about sort of 3 common ways to fabricate the transducers at the acoustic stack level, and we do all 3 of these types of approaches. The most versatile is hand wiring, and you see a photograph there of a hand-wired array, and this array probably has a pitch of a little over maybe 1.5 millimeters. And you can see where we've actually hand soldered wires to every element and then to an interconnect board. And this is the benefit of this type of technique is it's very flexible. It doesn't require large investment in tooling, and we can do it pretty quickly. However, as the pitch gets much finer, or we're doing higher volumes of arrays, the other 2 lamination types of methods become appropriate. And there's really 2 different general themes, although they're implemented in different ways. But is stack lamination with through backing interconnect, which is the upper right picture, and this shows you an approach where the backing has actual flex circuits that are coming through the backing and addressing the element interconnect perpendicular to the elements. This is a great way to do very high density arrays because it allows you to interconnect at a fine pitch, and it also allows you to have the piezoelectric material directly in contact with the backing, which is really the downside of the other technique in the lower right, which is stack lamination with a parallel flex. So here, the flex circuit is laminated between the piezoelectric and the backing. So this is a simpler approach than through backing interconnect, and it actually works very well for linear arrays, and works well for many matrix arrays. There's some limitations on the density that you can achieve, because there's only one layer of flex circuit to bring all the connections out, and as you start into having many hundreds or thousands of connections in a small area, and that can be problematic. But the downside is that the flex circuit is between the transducer element and the backing, so it has a slight performance disadvantage. But at any rate, these are three general options for how we can build arrays, and we consider this, depending on the application, we consider one of these three. Now, as I mentioned, the impedance matching the elements is also important in the transducer design. The element area is much smaller, and generally speaking, in a matrix array than a linear array, and causes the poor impedance match that I mentioned. So there's really several approaches where we can address that. First of all is we often create arrays using piezo composite material, so it's a composite of piezoelectric ceramic, PCT, and polymer epoxy. And by the volume fraction is really referred to as the relative volume of ceramic to polymer. So 30% volume fraction composite has 30% ceramic. Well, the ceramic is really the component there that drives the electrical impedance of the element, and so by using more and more ceramic or high volume fraction, that can help the electrical impedance matching of the element. We can also look at different materials. So traditionally, PCT5H materials are widely used in phased array transducers, for medical and for industrial. But there are several newer materials that are available that have higher dielectric constants. A couple are listed there. So whereas the dielectric constant of PCT5H is 3,400 to 3,800, we can get materials now that range 4,000 plus in dielectric constant, and can help improve the impedance matching situation for a phased array transducer. There's also recently been a lot of work in single crystal materials, and we're just starting to look into this, but it really, unlike using polycrystalline PCT, which is sort of traditionally what everybody uses, these materials are actually grown crystals or oriented crystals of PCT. They have better performance, better bandwidth, and they also are available in these high dielectric materials. So that's another thing that's been primarily driven by the medical community to improve matrix array performance, is single crystal materials development, which is now widely being used in medical transducers. Many industrial applications were using 128 or less channels, so matrix arrays that use less than 128, the standard cabling usually works. But sometimes we get into scenarios where we have more elements. This shows you an array that we did that has 840 elements. It's a 1.5D array, so there's 420 electrical connections. And we had to actually use 4 cables and connectors to interconnect that transducer. So generally speaking, as we develop very high channel count arrays, we can get into scenarios where we have to use more and more connectors or custom connectors in order to interconnect the transducer. Now, compared to linear arrays or more standard array geometries, matrix arrays, I think one of the biggest differences from the transducer design perspective is modeling, and the need to use modeling to evaluate all the trade-offs. So usually you have a limited amount of system channels available to you, or you have a certain budget on channel count, and therefore we still have to, we'd figure out what is the combination and geometry of the elements to make the sound do what we want it to do. So, as I kind of lay the problem statement out there, how do you get to the beam to go where you want it to go with the appropriate characteristics to detect what you want to detect, with the minimum amount of channels and expense, or with the number of channels that you have available. So modeling really becomes a very important tool, and whereas doing application development with more traditional linear arrays, I think modeling is certainly important, but I think it's not always needed. Whereas with matrix arrays, I think very oftentimes or always you need to use some modeling to try to get the array configured in a sensible way before you make any types of prototypes or investment. So at the end of the day, we need to evaluate trade-offs, the number of channels required for the application, the pitch in the aperture, the architecture, if you will, and any bad effects, based on what you've done, for instance, grading lobes and noise. So as I mentioned, I talked to you about one application that we did. This is a bolt probe application, and previously it was done with a linear array where the beam was swept into the thread area of the bolt, but you had to rotate the array in order to fully scan the bolt. So the idea of using a 2D array is to do the scanning electronically. We just have to put the probe on the bolt, electronically scan, focus, and sweep, and therefore and then create the images of the bolt thread and try to detect the defects that might be present. So the customer wanted to move in this direction, so they didn't have to manipulate the array, and we looked at 3 different options, including what we call a daisy type array, and then 2 different options on segmented annular with some different size constraints. In this case, we use SIVA to do the modeling to understand or to evaluate these different options prior to creating prototypes. This just shows you some of the things that we can do in that tool, where we can model the array, we can model the part, and even the defects. And so you see output here from the program where we can look at different simulated responses and even A-scans. Again, the idea of the modeling is in order to do that prior to prototyping, to get a good idea of your optimum design. So of the 3 that we chose here, we did modeling, we decided which was the most suitable approach, and then created a prototype. And this shows you some of the empirical results, showing the different notches. So again, a quick example, but it's just an example of how we the criticality of modeling and understanding what you're trying to do and how you're going to meet your goals prior to actually prototyping the transducer. So this slide shows you some of the different types of arrays that we've made here at Sensor Networks. 2 of the photos in the upper left and lower right show you dual, we'll call them 1.75D arrays, because the elevation dimension is a little bigger than the azimuth dimension. But these are sort of 2 different dual matrix array transducers for power generation inspection. The lower left shows you a high element count 1.5D array for forging inspection. This is actually an immersion transducer, so it's would be put into an immersion tank, and then using the matrix array to achieve focal depth over a variety of depth in the part, as well as to linearly scan through the array and create one axis of scanning. And of course, the other axis is by the turntable of the in the immersion tank. Also, 2D arrays don't necessarily have to be phased arrays. So in the upper right, an example of a very high element count spherical shaped array. This was for composite characterization. Each of these elements are only working individually, but nonetheless, it's a matrix array, an example of the types of things that we do here at Sensor Networks. So where does this all go from here? Through my work at GE Global Research, I had the opportunity to work with some of the medical transducer development folks, and they are well ahead in technology and very well funded to create different types of transducers and really do a lot of development work. And this is just an advertisement from Philips for their X matrix. So these are our actual transducers that were developed, and you can see just in this advertisement the channel counts they're talking about. So cardiac probe with 3,000 elements up to vascular probe with 56,000 elements. So here in the industrial circles, we're still oftentimes working with matrix arrays of less than 128 channels. We've done some higher channel count arrays. So I showed you pictures on the previous slide of the 840 element array, and we have the spherical transducer was 256 elements. But you see that medically speaking, they're going to very, very high element counts. And the way that they're doing that is by integrating electronics with the probe using what they call sub-aperture processing. So they actually have phase array processing in the probe handle that does some sort of pre-focusing for groups of elements, and then they're connected to high channel count systems with 256 and more phasing channels. As I mentioned on the materials slide, this is also driving different technologies around the piezoelectric materials, like single crystal materials, using quarter wave resonators instead of half wave resonators. So there's really a lot of technology being developed, and it's hard to say how that will impact what we do in industrial NDT, but certainly these capabilities are being developed and are out there, and I think gradually we'll see increased channel counts in our systems, and we'll be seeing more sophistication in our phased array transducers. So some concluding remarks. Matrix arrays, of course, are increasingly being used and developed for industrial applications. There's many trade-offs in the designs. Mostly channel count, based on the channel count. We always have limited numbers of channels to work with based on the systems we have, and so we have to decide how to, in a smart way, break these apertures up into a matrix of elements and get the performance that we're looking for. The smaller element sizes that we have in some of these transducers can require a more nuanced approach to the construction, the materials, the type of fabrication and interconnect. Some of the things I talked about with advanced materials, for instance. I think modeling is really essential for evaluating all these trade-offs. As I just showed you on the last slide, the medical array advancements show that there's really many, many possibilities that are well beyond sort of where we are in the state of the art in industrial applications. But as these new materials and techniques are fabricated on the medical side, I think they will filter down into industrial applications over time. So that's it for the webinar today. Thanks very much for your time. Please feel free to contact us with any questions around matrix array or other transducer needs. The contact information is listed on the slide. So thank you again for your time and attention today.